I'm going to prove that this function, where it's 0 on 0, 1, except at 1/2 it's 17 for some reason, is integrable on 0, 1. It should be 0, 1. And so if we want to draw a graph of this picture, it looks like here's 1, here's 0. I'll do this in green. It has a point way up here, and the rest of it looks like this. So it's always 0 except one point up there. Now my strategy for this is I'm going to choose a partition. I'm going to choose a partition. I have to pick the endpoints, and then I'm going to pick a couple points that are close. So in other words, right here I have the point 1/2. Here's the point 1/2 plus, let's call it delta, and here's the point 1/2 minus delta. So I'm going to pick delta so that I'm going to let p, I'm going to start over, 1/2 minus delta, 1/2 plus delta, 1. I'm going to pick delta such that UF of P minus LF of P is less than epsilon, which I defined way up there if you remember. And then that's going to be enough to prove that's integral, right? Because I'm going to use a theorem that says a function's integrable if for every epsilon, here's an epsilon, you can find a partition, I'm defining it after the epsilon such that this inequality is true. Well, let's actually figure out what U of F and L of F are. U of Fp is equal to, well, the first interval goes from 0 to 1/2 minus 1. So it goes from 1/2 minus delta minus 0. And then I need to plug in the infimum there, or the supremum, sorry. Plug in the supremum for the next interval times 1/2 plus delta minus 1/2 minus delta. That's the length, that's the distance between there and there, plus the supremum from 1 minus 1/2 plus delta, and finally plus supremum of, hey, that's it. Okay, we're actually done. So I just have 3 different spaces to figure out. And notice between from here to here, for the first one, the supremum is actually 0. Similarly for the last bit. The only interesting part is here in the middle. Between these two red points, 1/2 minus delta and 1/2 plus delta, my supremum is actually 17. So this boils down to 0 plus 17 times 2 delta, right? 1/2 minus 1/2 delta minus a negative delta plus 0 equals 34 delta. Great. L of Fp is going to be nice and easy. The infimum is 0 there, is 0 there, and is 0 there. So L of Fp is just 0 in this case. So I get that U of Fp minus L of Fp is equal to 34 delta. And if I go back up here and pick, I'm going to pick delta equal to, how about epsilon over 35. So then this is equal to 34 times epsilon over 35 equals 34/35 epsilon, which is less than epsilon. So F is integrable on 0, 1. So that's the basic strategy is if you have some sort of a weird function where you might have a discontinuity, you try to isolate these discontinuities by picking your partitions so that the distance between them is small. I'm going to do one more screencast that's going to give you a more normal function. And we'll discuss how to do that. So on the next screencast, I'll describe how to do a more normal function, one that might just look like, probably just be a line. And I'm going to do this like we did in calculus, but we'll see that ends up working out well. So we'll stop right there.